All right, let's get back to business. So, are there any other questions about the PDA to CFG conversion that we just, yeah. Uh-huh. So guys. So for number two and number three, when do you know when to check what you're reading or when to... So for rule types 1 and 2, I'm not looking at the PDA at all, other than the states. So that's just brute force elimination of the, enumeration of those two rule types. For the type 3, where we look at the pushes and pops, I'm looking at all pairs of transitions where it pushes one symbol and the other transition pops the same symbol. All pairs. Even if they make absolutely no sense, I'm looking at all pairs, just in case. Other questions? Yeah?
Would you say the total number of rules that would be created would be NQ?
Well, the first set of rules will always make n rules if there are n states, and the second one will make n cubed if there are n states. But the third type, what if there are no transitions in the PDA at all? Then it will generate 0. What if we had every single possible transition? Well, since we looked at all quadruplets of states, I may have n to the 4th transitions, possibly. It may be somewhere in the middle. So I can't definitively say how many transitions there will be, but I know it's at least n cubed plus n, for sure. Yeah, so the first one makes n rules always, second one makes n cubed rules always. Other questions?
So
yeah.
For 3, would you have one per transition or per?
I can't necessarily say because it depends on what the transitions actually are pushing and popping. Yeah.
Would you do them in the opposite direction too, or just the forward direction?
What do you mean in the opposite direction?
So like we have AQ0, Q3. Would you also do Q3, Q0?
No, not necessarily.
They're pushing and popping.
Yeah, because it's asymmetric. Other questions? Okay. So what did we do when we talked about regular languages? We talked about this machine model, DFAs and NFAs. Then we proved equivalence. Then we talked about regular expressions, proved equivalence for that. Then we looked at regular grammars. But we looked at something in between. What did we look at before we talked about regular grammars? We proved that some languages are not regular. So we looked at a grammar model for the context-free languages. Then we talked about a machine model, and now we just proved equivalence. So what do you think we're going to do next? Show that some languages are not, in fact, context-free. So let's talk about one language. So I'm going to talk about 0 to the n, 1 to the n. Well, if I stopped right there, we already know that that is context-free because we had a grammar for it. But I'm going to extend it to 2 to the n. So it'll turn out that this language is not context-free. But what would make it really hard for a grammar or a PDA to recognize this language? Well, an intuitive idea is, well, I have to push on the zeros in order to match them up with the ones, but then how do I match them up with the 2s at the same time? That seems problematic. Is that a proof that it's not context-free? No, there may be some other way that works. In fact, if I allowed you 2 stacks, could I recognize this language? Yeah, what do? Push the zeros on the first stack, push the 1s on the second stack, and then once I start reading the 2s, match them up with both of the stacks at the same time. So in fact, if we allow you 2 stacks, it's already going to be more powerful than the context-free languages. But that is not a proof that this is not context-free. So let's prove that it's not context-free. Well, what did we do when we talked about proving some languages are not regular? Well, we looked at a DFA, and we said if we feed this really long string, we had to repeat a state. And then what we tried to exploit is, if we repeated that part some number of times, then I'll get a string that shouldn't be in the language, but the DFA would have accepted anyway. And so therefore, that DFA could not have possibly been right for that language, and therefore there's no DFA for it. Let's try to do something similar here. Could I use a PDA to help me here? What could go wrong, though? Well, I'm not worried about the size. The problem might be the PDA is non-deterministic. And here's a more important thing. If I somehow was able to find a loop, am I guaranteed to be able to go around that loop again? No, why not? No, I'm not worried about what it chooses necessarily. Maybe the start transition of that loop had to require a character be popped. And then once I got it back around, I have a different character on top of the stack. And therefore, I can't do that transition again. It may seem that PDAs are a little problematic with this. So maybe let's not worry about PDAs. Let's talk about maybe CFGs, because are they equivalent? Yeah, so I can maybe talk about an arbitrary CFG. So let's let G be an arbitrary CFG. But maybe we can talk about, instead of repeating states in this machine model for PDAs or DFAs, maybe what could we repeat in a grammar? A rule, or more generally, the variable on the left-hand side of the rule. Maybe we can repeat variables in some way. Well, if I looked at an arbitrary CFG, then there's a problem. Well, not necessarily a problem, but the rules may be very complicated, right? The rules, I allow you anything on the right-hand side. And so maybe reasoning about what could appear on the right-hand side may make figuring out whether there's a loop in this CFG for variables very difficult. Do we have a way of simplifying the grammar? Chomsky normal form. Can any grammar be turned into Chomsky normal form? Yeah. Maybe we can look at CFGs in CNF. And so this is another application of Chomsky normal form, it'll turn out. All right. Well, I need to figure out in this CNF grammar whether there's some kind of repetition of variables. And then if there is, then I can exploit that as many times as I like. So what can I look at in order to see if there's a repetition of some kind? Well, what two ways of looking at a derivation in a grammar could I look at? Well, I could look at leftmost derivations and see a repeating variable. Or what's another way? Parse tree. Well, it seems like a parse tree is more graphical. And so like the DFA black box example, let's look at an arbitrary parse tree, because those are equivalent to leftmost derivations. Well, let's see. So let's say that this is an arbitrary parse tree for some string that G can generate. Because the grammar in CNF, could I guarantee anything about the structure of this parse tree? Oh, sorry? Well, I'm not looking at derivations here. I'm looking at a parse tree. So it's with these nodes with children, but could I guarantee anything about the structure of the parse tree because the grammar is in CNF? Well, first off, what is the top node? The start variable, let's call it S. But what do I know about the children of S? How many children does it have? 2. Does it have more? No. Why? Because it's in CNF. What do I know that the 2 children are? Are they variables, or are they terminals, or what? They're variables. If I make the string long enough, let's say. So I know that the 2 children are variables. What do I know about A and B here? in terms of what they are not.
They're not X.
They're not the start variable because the grammar is in CNF. Here's another nice property. Can A or B make the empty string?
No.
No. So A must make something of the tree, and B must make something else. It has to make the rest. B has to make something else of the tree. Okay? Let's see. Let's say that there are n variables in G. Let's say. Well, I want to repeat a variable in this parse tree somewhere. So, if I want to repeat a variable in this parse tree, how high must the tree be? At least n plus 1. So if we can guarantee height of parse tree is at least n plus 1, then the, without loss of generality, longest root to leaf path in the tree repeats a variable. If we can guarantee that, then the tree is so tall that the longest path from the root to some leaf must repeat a variable because I'm going to see n plus 1 variables along the way. Okay? Another nice thing. What do I know are at the leaves of the tree? The terminals. W1 up to Wn. Oh, I should not use n here because that's the number of variables. Let's call it k. Okay, so what does the tree look like, just to recap? It's the start variable at the top, and every internal node of the tree is going to have exactly 2 children, which are both variables, unless it's the variable right above the leaves in the tree, in which case it only has 1 child, which is that particular terminal. Okay, so if we take all the leaves off the tree, then the tree is going to have exactly 2 children, and therefore it's a binary tree. It's going to have internal nodes, which are variables, which have 2 children, which are variables, and they have 2 children, and all the way down. So, how many internal nodes of a binary tree do I need in order to guarantee that I have height at least n plus 1? 2 to the n plus 1. So if the parse tree has, not necessarily internal nodes, but the number of leaves at the bottom, so has at least 2 to the n plus 1 leaves, then height is at least n plus 1. Because if it was only n, then 1, then times 2, times 2, times 2, times 2, n times, the bottom must have 2 to the n children. Has 2 to the n leaves. But I just said that it has at least 2 to the n plus 1 leaves. And so therefore, I must have some path that has n plus 1 variables along the way down. Okay? So all I'm doing here is making the parse tree so tall that I must repeat a variable along the way down. And then now we're going to exploit that fact. But are there any questions so far? Yeah, sure, I'll do a recap. So we wanted to repeat a variable in this parse tree. And if there are n variables, I want to have some way that there are n plus 1 variables along the way down. Well, how can I guarantee that there are n plus 1 variables on the way down? Well, if I look at the longest path in the tree, that's certainly enough. So if I look at the longest path, how high must the tree be? Well, if I have it be n plus 1, then what is the worst possible number of leaves that I need at the very end in order to guarantee a height of n plus 1? Well, if the tree is completely full for n levels of the tree, then that means I have 2 to the n children at the bottom. But I just said, if I have 2 to the n plus 1, then I must have another level below that. And so therefore, I must have at least n plus 1 levels in the tree. And therefore, the longest path from the top to the bottom must be at least n plus 1. Yeah. Yeah, because I have n variables, and I just saw n plus 1 on the way down. And so therefore, there must be some variable that repeats. I can actually guarantee more than that, but yeah.
Okay, I missed the step from the 2 to the n at the bottom to 2 to the n plus 1. How
Yeah.
do we know that there's 2 to the n plus 1?
So if I force that the string that we generate has 2 to the n plus 1 characters in it, which are the leaves of the tree, then in order to generate it, it must have height at least n plus 1.
Can we just say that it has that many, the string that we generate?
That's what we're going to do next. Other questions? Okay, so let's try to exploit the fact that we made this tree so big that it repeats a variable. So I'm going to redraw that tree slightly bigger. So at the top is S again. And I've made this tree so tall that there must be some path that repeats a variable. So let's say that this is the path right here. It may be all the way to the right, it may be all the way to the left, it may be in the middle. I'm just supposing it's in the middle. Well, I said that a variable must repeat. Is that variable S? No, because S cannot be on the right-hand side of any rule. So let's say that the first occurrence of the repeated variable is A, and I said it repeated, so there must be a second occurrence of the same variable in that particular path all the way down. Could either of those A's make the empty string? No, because it's not the start variable. See why CNF is so useful here? So I know that each of these A's must generate something of the string. But could the first A make the same thing that the second A generates? You sure? Well, let's look at this in more detail. What is the closest that those two A's could be to each other? Well, A could be a direct child of the first occurrence. So let's look at that case. So here's A up here, and that's the second occurrence of A. And I don't care what the other one is, let's call it B. It may be A as well, but it's some variable. Could B make the empty string? No. And so, therefore, one of the sides of A must be non-empty, the first occurrence of A. It must be non-empty. Even if it coincided with the second occurrence of A, the other side must make something. Okay? In general, it may be that both sides are non-empty, but at least one is non-empty. Yeah.
So when you say repeated, do you mean like we're looking at like the grammar, all the grammar rules?
Mhm.
Would that mean that A would appear twice on the right hand side somewhere?
It will appear in the derivation twice. Because if you think about it, we're doing a partial derivation going down this tree, this particular path. And so by doing this, we have the variable A appearing twice in the derivation, in this partial derivation.
So like if we were doing like a leftmost cross, we'd see it twice.
At least, yeah. Yeah, so appear in the sense that it comes into existence. Not in the sense that like you apply a rule, it is still there. You mean appears in existence? Yeah, that's true. Other questions? All right. Well, so therefore, at least one of these two sides is non-empty. It may be that both of them are non-empty, but at least one of them is non-empty. Okay? Well, let's see. Let's give these 5 parts names. Let's call the first one U, second one V, third X, fourth Y, fifth is Z. Well, let's see. What do I know about V and Y? Can they both be empty? No, because of the argument that we just did. They can't both be empty because of this up here. So we know that V and Y are non-empty. So another way of saying that is that together they have at least one character. So I'll write the other way. V and Y are not the empty string. It means the same thing. Yeah.
So why can't you answer the empty?
They could. They certainly can't be. I'm not restricting them.
Why can't they? Like what makes me one?
Because if the second occurrence of A happens to be the second occurrence of A is the direct child of the first, then the other child of A must make something of the string. And so whatever side that is, it must correspond to V or Y. And so therefore, it must make something of the string. And since they can't generate the empty string, one of those two sides must be non-empty. Yeah.
If they can't generate the empty string, how do we, what would be an example of one of them being empty?
In this case up here, Y would be the empty string. Because the second occurrence of A corresponds to the first one on the right side.
So there would be no Y.
Yeah, in that particular case, yes. And if you flip A and B across, then V would be empty.
Quite connecting how they coincide. Is it just that?
So if you look at this, so if A is right here, this is the second occurrence of A, this is the first, this is B right here. Well, B must make something of the string, and A must make the rest of it. So the second occurrence of A the right side of the second occurrence of A corresponds exactly to the right side of the first occurrence. The right-hand side of this subtree matches. But if it were different in the sense that we have A up here, and then A is somewhere in the middle, then they don't correspond because some other variables, let's say B and C, they may make something else of the string. Yeah, so if they were both empty, then that would mean that the second occurrence of A and the first are the same occurrence. Because one of them fell lower, then it must make the other side, since it has two variables, the other side must make at least one character. So it can't make, the second occurrence can't make everything the first did. Yeah.
Now, also due to the rules about you can have repeated rules, that second A doesn't necessarily need to make the
Yeah.
A, right?
Yeah. The second occurrence of A, I'm not saying anything about it. It's just that along the path, the variable repeats.
Okay.
Yeah, I'm not looking at the rules here necessarily. Other questions? Okay, well that's neat and helpful. So that's one thing we need to keep in mind. Well, let's see. So I'm gonna copy this tree down. Let's see. So maybe we can talk about what the strings that S can make are. Well, what could this second occurrence of A make for sure? What's one string that we know it could make? I'm not looking at that yet. What about this subparse tree? Could A make the string X? Yes. So it certainly could make X. What else could that variable A generate? We'll look at the first one. Well, it makes V, then whatever A could make, then Y. Oh, okay. So it makes V, A, and Y.
What's the asterisk?
Yeah, so I covered this in a previous lecture. That just means 0 or more rule applications. It actually has to be at least one here, but I'm not concerned about that. Okay. Well, in this tree, what could S generate? Well, could it make U, A, Z? Yeah, it could certainly make U, A, Z. Could it also, for instance, make, let's say, U, B, A, Y, Z? Yeah, certainly. We go to U, A, Z, and then we apply A makes V, A, Y to make U, V, A, Y, Z. Oh, what if could I make U, V squared, A, Y squared, Z? Sure, yeah, I apply V, A, Y again. Oh, what could we say about U, B to the I, X, Y to the I, Z? So let's see. How do I get that string? Well, I apply S goes to UAZ. Then we apply A makes VAY I times. And then we apply A makes Z. So what could I say about the string UV to the I, X, Y to the I, Z? It's in the language. Why? Because I can make a parse tree for it. I can just iteratively apply these rules over and over in order to get it. Oh, so we know that U, B to the I, X, Y to the I, Z is in L for, sound familiar? Mm-hmm. There's one more that we need to look at. Let's look at this first occurrence of A and this sub-parse tree right here. Okay. Suppose that the entire string U, V, X, Y, Z has the absolute minimum number of characters to make the tree tall enough. Suppose it has the absolute minimum and it can't go any lower. How long could VXY be? Could it be the entire string, possibly? Could VXY be longer than the length of the minimum number string? No, it can't be longer. What if I had a possibly much longer string that's not necessarily the minimum? Could I have VXY be longer than that, whatever that minimum was?
Yeah.
Well, if you look at the bottom n+1 variables, there must be a repetition there. I don't have to look at any higher variables, I just need to look at the bottom n+1 of them. So if I look at the bottom n+1, I have a repeated variable. So I can guarantee now that VXY is not too long because it corresponds to the repeated variable. So now we can prove, we actually just proved something we call the pumping lemma for CFLs. Okay, well, let's see. Let L be a CFL. And this will go almost the same as the regular languages one. Then there exists a pumping constant P for L. Well, again, how did I get to this point? Well, we had to guarantee that there was a repeated variable. Well, how did we make the tree so tall? Well, we made it tall because we considered a string in the language of the grammar such that it has length longer than a certain value. So we need to look at all of those strings. For all W in L with length of W at least P. And P in this case will correspond to 2 to the number of variables plus 1 for any grammar for L. But we're not concerned with what the value is necessarily. Well, we looked at all of these strings that are long enough and in the language. So that for all strings that are long enough and in the language, there exists a way to write W as U, V, X, Y, Z, so that. And then here we'll have 3 conditions like before. Well, what's one of the conditions? The length of Vy here is at least 1. Okay, so that's the second condition. So here, now we're going to be worrying about 2 parts of the string instead of 1 being non-empty. What's another condition that we were able to deduce? Yeah, you're right. So if I pump in I copies at the same rate for V and Y, then that'll always stay in the language. So U, V to the I, X, Y to the I, Z is in L for all I, at least 0. And then what was the third one that we were able to deduce? The length of the 3 middle parts is not too long, because if we only look at the bottom n plus 1 variables of that root to leaf path, then there must be a repetition among those that sub-parse tree. And so therefore that parse tree can't be longer than p characters. So Vxy has length at most p. Any questions? So everyone fully gets it, right?
Oh yeah.
I am going a little fast, so remember, you always have the right to say we want a minute of catching up. That's totally fine. If you.
So the length of Vxy kind of corresponds to the earliest point in time where the repetition.
Yeah. So look at the bottom 2 repetitions of the variable, and if you look at the top one, it has to be within the bottom n plus 1 variables because of the repetition thing. And so therefore, this p constant corresponds to the bottom n plus 1 variables. And so it can't be longer than that part. It could be the entire thing, but it can't be longer. So Vxy can't be too long. Okay? Yeah. So P will represent the number of characters of the leaves of this parse tree. So remember, we made the parse tree so tall because we made the number of leaves very large. And if you want an actual value, for any grammar for L, if n is the number of variables, then P here will be at least 2 to the n plus 1. But the constant's not that important here. Other questions? Yeah, sure. So I'll definitely do an example because we are a little ahead. But the intuitive idea is the part that you're pumping is not too long, but can appear anywhere because of how the derivations work. I can't necessarily guarantee where the longest root to leaf path is. It may be all the way on the left or all the way on the right or somewhere in the middle. But I know the repeated part can't generate very much of the string. It can only generate up to p characters. The second occurrence of that repeated variable forces that the difference between the first and the second occurrence have one of those two parts be non-empty. So Vy is at least 1 in length. And if we put another subtree, if we copy that, so it's actually good with an example. So if we have this repeated occurrence like this, so this is A, this is the second occurrence, in the past like that. Well, what I could do is I can take this parse tree, this outer parse tree, and substitute it right there. So then I can make an even larger parse tree that looks like this. And then, of course, I'll now have another occurrence of A because I copied it down. So what is this? Remember, it was Vxy from before. So this is V, oh, this is V here. Well, I'm still going to generate the same things. So I'm going to have Vxy right here and another Y right there.
And the U zone is very outside. Right?
Yeah, I'm not worried about that yet, yes. So so this is just a graphical representation. If I do this copying process over and over, then I'm going to get another copy of V and Y every single time. So the number of copies of V and Y are always going to be the same. Okay? Any questions? Okay, so let's prove a language is not context-free. So show that 0 to the n, 1 to the n, 2 to the n is not context-free. Proof. If I want to show a language is not context-free, how do I do it? Assume it is context-free. So let's say I call it L. Then assume L is CFL. Then what? There is a pumping length P for L. So the way these start out is almost identical to how, in fact, almost the entire process is identical. But how you think about the cases in the middle is going to change very slightly. But the process is almost the same. Okay, well, we picked this pumping length P for L, or there exists one. What do I do now? Let's pick a string. So let's choose some string. What two properties do I want of this string? Is at least P characters and in the language. Do you think I'm going to test for that? Yes. So pick a string in the language and long enough. 0 to the P, 1 to the P, 2 to the P is a perfectly fine string. It has at least P characters. Is it in the language? Yeah, it has the same number of zeros, ones, and twos in that order. Okay, well, let's see. So what I want to do is I want to show that for every decomposition, I can pump out of the language. Well, we don't have it quite as easy as when we did it for regular languages, because there we can only pump within the first P characters. But here, can I guarantee that? No, the VXY part can be anywhere in the string. But how long could it be? At most P characters. So for any decomposition of W into UVXYZ, well, could VXY be entirely in the zeros part? Yeah, certainly. Could it be all in the ones part? All in the twos? Have some of the zeros and some of the ones?
No. 1/3. Yeah.
Yeah, it could straddle between the zeros and ones. Could it have some of the ones and some of the twos?
Yeah.
Could it have zeros, ones, and twos? No, why not? It'd be too long. So we can see that VXY cannot have a 0, 1, and a 2. It may have 2 of those characters, but it can't have all 3 of them. So now we got to figure out, if I pump in an extra copy of V and Y, what could happen? Or take one out, or some other number of pumps into V and Y. So let's consider U V squared X Y squared Z. So this may seem like a tough question, but it's really easy. What is the only way that that resulting string could be in the language? In order to be in 0 to the n, 1 to the n, 2 to the n. Well, what is the only way it could possibly ever be in that language? If it has the same number of zeros, ones, and twos. That's the only possible way. If it has a differing number, then there's no way it's in the language. So if it is in L, then the number of zeros, so I'm going to call this string S because I'm going to write it several times. So the number of zeros in S equals the number of ones in S equals the number of twos in S. That's the only way. There are other things that has to be in the language, but that's at least a necessary condition in order to be in the language. Well, what happened when I pumped some character? One of those must have gone up, right? Because, what is the condition? Because I pumped in, I must have gotten at least one character in. V and Y had length at least 1. So I pumped some character in. So because Vy has length at least 1, one of these 3 values increased by at least 1. That's the only way that could have happened. But if it's in L, all 3 values must be exactly the same. But because so how should I say this? Because Vxy cannot contain a 0 and a 2 simultaneously, then Vxy only contains 1s. That's the only possibility. We must have not increased either of 0s and 2s, because those 2 values must be the same in order to stay in the language. But if Vxy only contains 1s, what happened? That's the value that must have gone up. This implies the number of 1s in S increased, but number of 0s in S did not. So now the number of 1s in a particular string increased, and the number of 0s didn't increase. So what can I say about that string? There's no way it could have been in the language because you have to have the same number. So S is not in L. And then therefore, what can I conclude? L is not a CFL. Because we handled every decomposition. into those 5 parts. So let's recap. I handled every decomposition here, and I said, well, what if you pumped up? Well, the only way you could have stayed in the language is, among other things, it has the same number of 0s, 1s, and 2s. Well, in the original string, VXY could not have had a 0 and a 2 simultaneously. So there's no way I could have pumped one of those numbers, one of those 0s or 2s. So the only possibility of that is if VXY is entirely in the 1s, which could be possible. But since I pumped in characters, the number of 1s must have gone up. But the number of 0s and 2s didn't go up either. And so therefore, there's no way it could have been in the language. Yeah?
I'm still not sure why it couldn't have straddled 0s and 1s or 1s and 2s.
Because in order to be in the language, the number of 0s and 2s is the same. So if it straddles the 0s and 1s, the 0s and 1s went up, but the number of 2s didn't go up.
Right, but don't we have to consider that decomposition?
I am, yeah. So in order to stay in the language, the number of 0s and 2s are the same. But any decomposition that doesn't increase them both simultaneously, which is every single one, that doesn't work. So,
Okay.
so it could
you're
only,
generalizing by saying the 1s.
yeah.
Okay.
So you possibly say it also because we don't have a string that would include both 0, 1s, and 2s.
Yeah, that has
they
like,
all
yeah.
not increase at the same time.
yeah. A much easier way to say this is all 3 values can't increase simultaneously.
So why is it that VXY can't have 0, 1, 2?
Because there's a string, the 1s have length p. So if I had a 0 and a 2 also, VXY has to have length at least p plus 2. And then therefore it can't be possible. That's why the design of the string is important, so that each of the parts in this particular case has such a long length that I can't pump all of them simultaneously. In fact, if we made this string shorter by having like p over 2, p over 2, p over 2, it would still work. How would it work? If you had 0s, 1s, and 2s, then if I put in an additional copy, among other cases, then you'll have a 1, 0 substring or a 2, 1 substring. But so there are other cases than that, but that's most of the way there. So you can still prove it, but here we made it easy for ourselves because we wanted to have all 3 values in this VXY substring to be impossible. Yeah, other questions? Yeah.
Just to completely clarify,
Mhm.
you say this applies at least one of the 0s, 1s, or 2s increased, but one of them didn't.
Yeah, well, in order to stay in the language, all 3 had to go up by the same amount.
As a answer that
Yeah.
would be acceptable.
Yeah, yeah. You should be a little more formal than that, but that's most of the way there. Other questions? Okay, let's do something that will help us get some more information about the CFLs. Well, are the CFLs closed under union? Yeah, how would I do it? Have a PDA for both of the corresponding CFLs, new state, triple epsilon my way over to both of the start states. So it gets us union. Concatenation, how would I do that?
Make sure final state not final, that triple.
Yeah, but the problem there is that there might be something on the stack still.
So we have to loop first if that.
Yeah, so that's a way. Another way you can do it is if S1 is the start variable of the first grammar and S2 is the start of the second, that gets us concatenation immediately. So this is for concat. What about star? Well, we can do this with grammars easily by making the empty string because that's always in the start of any language. Or pick a string out of the original grammar and try again. So if S1 is the start variable of the grammar for whatever language we're considering, then we get closure under cleaning star by saying make the empty string or make something out of that the grammar would have already made and then go back and try again. So it's just like the NFA thing that we have done for star. So this is for star. And actually I'll do another way for union. You can do S goes to S1 or S2 for union. But PDAs can actually do all three, but there are some things you need to worry about for the stack. But so grammars and PDAs have their own trade-offs in terms of what you can do with them. Okay? Can we do intersection? Well, we may want to try something like the what construction that we did with DFAs. Product construction. What would seem like a problem if we just tried that here? Yeah, if we have two PDAs with conflicting stack operations, I don't know what to do. Because the thing I have to have at the end is a PDA, and it only has one stack. If I have two stacks, then I can do it. But one stack, I can't necessarily do it that way. And it turns out they're not closed under intersect. Let's see why. Well, remember the language that we just talked about, which is 0 to the n, 1 to the n, 2 to the n, and at least 0. But instead of all three being equal, could I recognize two of them being equal, and the third one being some other number? Yeah, I can certainly do that. So let's consider the languages L1, where the first two numbers are equal, and L2, where the last two are equal. Can I make a grammar or PDA, if you want, for both of these? Well, I actually argue it's pretty easy. So here, can I make a grammar for 0 to the n, 1 to the n? Ignore the 2 part. Yeah, so that's actually pretty easy. So I'm actually going to move this down a little. So I'm going to have A make that part. So we had a grammar for 0 to the n, 1 to the n before. Can I make a grammar that just spits out 2's, ignoring anything else? Yeah. So I'm going to make a grammar that just spits. In fact, we can make a regular grammar for it, which is nice. So, oh, not 0. 2. In fact, we can make a regular grammar for it, which is nice. So, can I make a grammar for L1 based off these two? Yeah, I would just generate whatever A wants to generate, and then whatever B wants to generate. Oh, what is that process? Concatenation. Are CFLs closed under concat? Yeah. So I just need to make AB. So the A part is going to make the 0 to the n, 1 to the n part, and B is going to spit off the 2's, just some number of 2's. Okay? Can I make a grammar very similar to this for L2? Yeah, all you need to do is swap the right-hand sides of A and B and replace A with B and B with A. So we can actually do that here. Actually, no, that's not quite right. So the A part just got to spits off all the zeros at the beginning, just like the B one in the first grammar did for the 2's. And B's got to make the same number of 1 and 2's. And so that's a grammar for that. So that actually wasn't that hard. But what's their intersection? Well, it has the same number of zeros and ones and the same number of ones and twos.
So it's all the same.
It's all the same. Oh, did we see that that language is not context-free? Yeah. So L1 intersect L2 equals 0 to the n, 1 to the n, 2 to the n. But this is not a CFL. Okay. One more before we close up. What about complement? Can I relate union and intersection and complement really easily? Look to our old friend, Augustus de Morgan. How do I relate complement and union and intersection? Well, we have intersection is just equal to the union of the complements, the whole thing complement. So that's De Morgan's law, or one of the laws. Are CFLs closed under union?
Yes.
Yes. If CFLs were closed under complement, what do I have here? I get closure under intersection, but do I have closure under intersection? Nope. So this implies no closure for complement. And so you may be kind of annoyed that that doesn't give us an example. So I'll break right here, but the example to think about is 0 to the n, 1 to the n, 2 to the n, complement. Can you, and so an exercise before next time is make a grammar for that. Okay? And so therefore, the complement of that would have to be something that's not context-free. Any other questions? Yeah.
On the layer above there, but it's not CFL, that's a particular thing.
What's there?
You said for L1 intersect L2,
Mhm.
but this is not CFL.
Yeah.
It's a regular thing.
No, no. I'm just talking about the languages there.
Oh, that's right. Sorry. If it's not, what is it?
It's definitely not context-free.
Okay.
Okay? And so therefore, it's not regular either. Okay? All right.